And we're back. Now, for this short video, we're just going to talk about applications of double integrals and improper double integrals. And then next time we meet, we're going to talk about double integrals and polar coordinates. All right, so there are many applications of double integrals on non-rectangular regions. Some of those are discussed in the textbook, and I'm just going to mention a couple here. So we can find the volume of the solid that lies below a surface, C equals f of xy, and above the region D, right? And that's just by evaluating the double integral of f over that region. To find the area of a region D in the xy plane, what do we do, right? We just integrate 1. So these should look familiar from what we talked about when we were looking at integrals over rectangular regions. And finally, we can find the average value of a function, and that's just given by 1 over the area of our region times the double integral of our function f over the region. And so these are really similar to what we talked about in the previous section. So I'm not going to do any examples here, but you can look back at those examples and see what we did. The next thing I'm going to talk about is improper double integrals. So that's when either our region is unbounded or our function is unbounded on subset of D. Now, the nice thing here, as opposed to when we were talking about these things in Calc 2, is that sometimes changing the order of integration will at least solve the second problem, and that would be the f being unbounded. If D is an unbounded rectangular domain, then the strategy for computing an iterated integral is pretty much the same as what we did in Calc 2. So I won't actually review explicitly in detail that. But let's look at an example here. So let's evaluate, or at least set up, the integral over our region D of e to the x over 3 plus y over 5. And our region that we're integrating over is x less than or equal to 0, y less than or equal to 0. Okay, so let's do this. So our integral of our function is the integral from minus infinity to 0 for x and for y of this guy. And what we do is we replace the infinities by constants. Dy dx, like so. And then we would do our integral as normal and then take the limit. So I'll start this one off, but I'll leave it really as an exercise for you. So if I'm integrating with respect to y, that's going to give me 5 times the integral of e to the x over 3 plus y over 5, evaluated to our limits. And I didn't leave the room for the whole problem because I didn't actually intend to do it. So we have the limit as AB goes to minus infinity, infinity, case minus infinity, minus infinity. All right, so this is going to give me the integral from a to 0 of 5e to the x over 3 plus 5e to the x over 3 plus b over 5. And when I do that integral, I'm going to end up with the limit as AB goes to minus infinity of, sorry, that was supposed to be a minus there. Let's just pretend I know what I'm doing. And then this one's going to give me the integral of, let's see, so that's going to be 15e to the x over 3 minus 15e to the x over 3 plus b over 5, a to 0. So finally, that's the limit as AB goes to minus infinity of 15 minus 15 e to the b over 5 minus 15 e to the a over 3 minus 15 e to the a over 3 plus b over 5. So since I'm taking the limit as a and b go to minus infinity, everybody cancels, and I'm going to be left with just 15. Now you should double check, make sure I didn't make any mistakes. And as usual, we have some suggested exercises from the textbook, and the next video is going to be on double integrals in polar coordinates. Have a great day.